We had two kinds of velocities. Now let's look at something called speed. Speed and velocity are used interchangeably in everyday language, but they have a different meaning in physics. Okay? Average speed, it is really just the distance covered in some time interval delta t. So like average velocity, it depends on an interval, but it's not velocity, it's speed. So to think about this one, let's do another example. Example 4 of Hal's motion. All right, example 4 is going to look like this. So Hal is going to start somewhere. We're not going to do the numbers this time. It's going to start somewhere and roll kind of slow in the positive direction and then really fast in the negative direction. Right, so think about that motion for a minute. Slow positive for a long way and then fast negative. Okay? Let's make a plot. Here we go. Example 4. Time x. Slow positive like this for most of the time. And then sharp negative. And gets down to some position. Right? There it is. There it is. So let's look at that and think about, let's look at the average velocity. What would that be? For the entire trip, what's the average velocity? For the entire trip, we could call this Ti. We call this Tf. Okay. What would the average velocity be? Well, it would be x final minus x initial over t final minus t initial. That's what it always is. Right? But if you looked at it, you could say we could do our little lines. There's x initial, and then here is, oh, that's supposed to be straight. Here is x final. So you can see he actually didn't get very far. Right? I started him sort of here, and he went, and he came back faster, and I stopped him here. So even though he went all this path, he only got this far in terms of displacement, in terms of a vector displacement forward, like that. So what I conclude from this is that it's slow. Right? I mean, we're not putting numbers to it, but you get the idea. He didn't get very far. Okay. Now let's look at the speed. Right? That's the average velocity. Let's look at the speed. V, average. Yes, we use the same symbol, but I don't put a vector on it. Okay? Velocities are vector quantities. Speeds are not vector quantities. So the only difference I'm making is I'm not putting the symbol, the vector symbol. So you got to remember. And you'll see why it's not a vector is because it's not a displacement vector. It's just d. It's just the total distance traveled over delta t. And you know distance doesn't care about direction. It's just how far did it actually go. And since it doesn't care about direction, it can't be a vector. Right? So no vectors on the average speed side. So to get that, we would have to break this up into a few parts. Right? We would have to say, let's call this T1, and this important point here, T2, and then here at the end, we call that T3. And then we can start relabeling these. And see, for speed, we'll call this x1. All right, we'll call this x2. And oh, we got really far out here, right? You got to x3. All right, so then we would say, okay, in this case, how do we get this distance? Oh, how far did it go? First, he went from x1 all the way to x3. Right? x3 minus x1. And then how far did he go? Then he went all the way from x3 to x2. If we do final minus initial, x2 minus x3, we'll get a negative number. And we want it to be positive. So I'll just do a little trick on you. I'll do x3 minus x2 plus x3 minus x2. I should do the other one and put magnitude bars over it, but people freak out, so I don't want to. But the point is, I did both of those numbers where they're nice, big positive numbers, big numbers, right? Over it'd be T3 minus T1. So you can see this will be faster, right? This will be fast. In centimeters per second. Also this, of course, they're all in centimeters per second. This will be faster because the numerator is much bigger, right? If we were to apply this idea to 1, 2, and 3, the average velocity, it would just be this little distance. Yeah, 3 minus, oh no, that's a 2, and that's a 3. Hopefully you noticed that and you smugly sat back and enjoyed my error. But I'll just keep going. Right, that's a 3, that's a 2. So really just be the small difference, 3 minus 2. That's why it's slow. Whereas this one has all these parts in it. That's why it's big. Okay. So speeds often are faster than average velocities because they don't have all the vector part in them. So it seems a little confusing. We have average velocity, instantaneous velocity, average speed. We have all these things just for the simple idea of motion. So what I like to do is take them and sort of put them all on a chart. Let's do a chart and see what we come up with. We're actually going to discover there's a fourth one. So I like to draw the chart kind of like this. Let me see, and I'm going to draw something like this and something like this. And I'm going to write velocity here, velo, and I'm going to write speed here. And then I'm going to write average here and instantaneous here. So first let's just remind ourselves what they are, right? The average velocity, that's what we called v, avg, and it was the displacement over some time interval. We got that down. And then we said, oh, let's let delta t be really small. And then we said that was the velocity, the instantaneous velocity, no subscript, but a vector symbol. And that was dx, where position, of course, is a vector, dt. We turned it into a derivative just by making delta t small. And then we said there's this thing, the average speed, right? And we put the avg, because it's average, but no vector symbol, because it's not a vector. It's just the distance traveled over delta t. So you could look at these and say, okay, then what about the instantaneous speed? What does that really mean? Let's draw a couple of xt plots here. So here's time, here's x, we got a ball that's moving, right? So you could say, well, let's see, instantaneous speed, what must that mean? It's like the slope, but it can't be a vector, right? It must be a v, beautiful cursive v's, no vector, but what's it equal to? It's kind of like the slope, but it doesn't care about the direction, right? So it's clearly the slope. What if we thought about it going up and we thought about it going down? What if we thought about a ball rolling both ways, right? So this is rolling to the right in a HAL demo, and this is rolling to the left in a HAL demo. The difference in v would be the sign, right? So here v would be, say, let's just estimate that it was 3 meters per second. I'll put I hat, positive direction. And here, let's say the instantaneous velocity would be minus 3 meters per second, I hat. But what the speed would say is it's just 3, because speed doesn't care about the direction, right? All speed cares about is how fast it's going. So speed would be similar. The instantaneous speed would also be sort of the value right at a point, but it wouldn't care about the sign. So the way we write that in physics is we just say, we take the vector and we just take what we call the magnitude. We put these 2 bars on it. And that's the magnitude of the speed. So if this is 3 meters per second or minus 3 meters per second, when you put these on it, it's just 3. It's how long the vector is, not which way the vector is pointing. So this really is the notation. So we rarely really talk about the instantaneous speed, or well, we do, but we don't usually write it like this. Right? A lot of times we would just say v, right? Instantaneous, no vector. But formally, I want to write it like this. It's a vector, but it's just the magnitude of the vector. So if you can have all these down, you'll be in good shape because we'll use them all later. And now to help think about them, let's think about sort of like their relationships. Right? When can you say they're equal? Are any of them ever equal? Let's see if we can go this way and make them equal. Right? When are they equal this way? Well, let's do a little wiggly arrow out here and say when they're equal that way. When are they equal going down? When they're equal going down for uniform motion, or when delta t is very small, right? So if you have your average velocity over, if things moving uniformly, we talked about how your average velocity between this interval and your instantaneous velocity at any time is the same, even if it's curved a little bit. If you look at a small enough interval, you're going to get the same average and instantaneous velocity. And the same thing for speed, right? In that case, it's not really any different. Okay, so uniform motion, these are indistinguishable. If things are changing their speed, then it changes. What if we try to go this way? What if we were to say, are these equal? What is the answer for that? And that's really a question of what do you mean by equal? Really, that's getting to this whole vector versus scalar question. Does it have a direction or not, right? So basically here you would say, yes, they are equal, that v is the magnitude of v, right? So they're equal in that sense. They have the same magnitude. This one is kind of interesting. If you go on a path, delta t, will the average velocity and the average speed be the same? Well, they could be, but they don't have to be. The way we would write it mathematically would be like this. Let's think about it for a second. Say we have one of the crazy paths, t, x, and it does something like that. Remember that? Where you have t initial and t final. The speed was bigger than the average velocity because the speed considered the whole trip. The average velocity just considered the short negative path displacement from here to here. So the speed was bigger. But the speed won't always be bigger. If you have a uniform motion and you look between here and here, they'll be the same. So the way you could say it is that the average velocity, v average, will always be greater than or equal to the magnitude of the average velocity. So I'm sorry, the average speed will always be greater than or equal to the magnitude of the average velocity, right? If it's a curvy path, the speed will be bigger because it went farther in terms of distance. If it's a linear path, then they both went the same distance and displacement, and they'll be equal, so greater than or equal. So this isn't super necessary to solve problems, but it does help you kind of get the big picture in your head of the differences of these things. At least in my head. It may not help you at all, I don't know. So far we've spent a lot of time on definitions of distance and displacement and velocity and average velocity, all these things. We haven't really talked about how to do kinematics or about the standard equations that you're familiar with or maybe that you've memorized before in kinematics. So now we're going to show you the link between the definitions and the useful equations. And we're only going to do it for right now constant velocity. So you do kinematics under different assumptions. Right now we're doing the kinematics assuming that whatever's moving moves at a constant velocity. And I wrote a quick problem here for us to use as we derive things. So a football player starts on the 10-yard line, runs at 8 yards per second for 4.5 seconds. Where does he or she end up? Which yard line? This is clearly American football. All right, so even though we're doing this and going for the equations, it's still usually good to draw a graph. Why not? So let's remind ourselves what this would look like, more or less. A kinematics plot, of course, has time. On that axis, x, we can say, is the position or progress down the field. They started at the 10-yard line. So we can start here at 10, where that's in yards, and that's in seconds. And we went at a uniform speed, so looks like that. And we know they stopped, or the part we care about, is up to 4.5 seconds, or this is the origin, like that. So that would be the plot. So really the question is, how far did they get? All right. So one thing we want to realize, it helps the notation, if we realize or remember that at constant velocity, so if we're at constant velocity, that the average equals the instantaneous. Remember, average is sort of the average velocity if you consider 2 points in time. Instantaneous is if you consider an instant in time. But as long as it's uniform and constant, it doesn't really matter. They're equal. That helps our notation because then we can say that v, the vector for instantaneous velocity, equals the vector for average velocity, which equals the displacement over delta t. I want to use this for the velocity. I want to think about just the regular old instantaneous velocity, but I want to have this formula. But this is for average. But actually all three are equal in this case. So we can go from there. We can remind ourselves, let's see, what is v? V is just v, the velocity. What is this? This is the final position minus the initial position over delta t, like that. All right, and then we can, let's see, we have a question. Let's see what the question is. And it is from Dank Mimes. Why is position a vector? I thought displacement was the vector. Okay, now I know what you mean. Here it is. Yes, so we define displacement as a vector because it's from one place to another. It clearly has a direction. These are positions, but they have to be vectors because this side is a vector. Right? So really, even though we introduce displacement as the vector, position is also a vector. Position is displacement from the origin. Right? So positions are also vectors. It's just, at the very beginning, we didn't describe them as vectors just to not confuse you. But positions are also vectors. Positions are just displacements from the origin. So if the origin is here and the first position is 10, there's the vector right there. That's the vector. So everything's a vector. And it is, yes, it is unusual. I'm writing all this in vector notation when it's a 1D problem. But that's how I decided to do it. Okay, so down here, also delta t, I should have written as time final minus time initial. So I could point out usually time initial is just 0. We're going to put something at the origin. It's usually ti, initial time is 0. And then usually tf we just call t. We usually are going from time equals 0 to some time t. That's how we would usually write it. So if we get rid of that and just call that t and then start switching things around, we can solve for xf, the final position in this problem. It's the initial position, right? We're bringing this over here and bringing that over. It's the initial position plus that constant velocity times time. And that is one of the standard equations of kinematics. That is the constant velocity kinematics. What is the position? You may know the street version of this. If you learned this in an earlier physics class, you may have just memorized d equals vt. Right? It's really the same thing. It just doesn't have the vector notation on it, and d means xf minus xi, sort of how far you got. And to use it, it's just a straightforward plug it in. The final position. Final position is the initial position, which was 10, the 10-yard line, plus the speed, or the velocity in this case, 8 yards per second, t, 4.5. All right, so 8 times 4.5, 32 plus is 36. 36 plus 10 is 46. So it's the 46-yard line is where they ended up. And since it's a vector, I'll put I hat. We'll say I hat is the unit vector for downfield. All right. Okay, so that's your first kinematics equation that you may want to know for constant velocity only.